So as always, I'm going to go ahead and record this meeting. And then as soon as we're done and it's done, finished being uploaded and processed and all that stuff, I'll post the video recording of me going through the notes with you guys on this Electron Shells Reactivity tab under the Zoom meeting recordings. So if you ever want to say like, hey, what did we talk about a couple days ago? You can go back and look for 917 Electron Shells, and that's where this posting is going to be. And as always, if you want to go back and read back through the notes, today is September 17th, which is a Thursday. And so these are the notes that we're going to be talking about today: electron shells and reactivity. So we're going to be continuing on with talking about atoms. And specifically today, we're going to really be focusing in on the electrons of those atoms. So let's get to it. All right, make sure we're still on the correct screen. Looks like it. Perfect. All right, electron shells and reactivity. Delving a little bit more deeply into the world of those electrons, those teeny, teeny, tiny negative particles that are all kind of zooming around the outside of our atom. So if you remember when we talked about electrons on Monday, no wait, this is Tuesday, Thursday class. On Tuesday, man, I have two different IPC classes on 2 different days, and I always feel like I get mixed up which one is going on when. So on Tuesday, we went over the protons, neutrons, and electrons, and we talked about how electrons are negatively charged. They're not in the nucleus, they're on the outside of it, and the electrons and the protons always balance each other out. So we talked about how the protons are positive and the electrons are negative. And in the atoms that we're going to be dealing with in this class specifically, we want to have neutral atoms. We want to have the positives and negatives balance. So we're going to say that however many protons an atom has, it's going to have the exact same number of electrons. Right? So for example, for hydrogen over here, the most simple and basic atom that there is, he's got an atomic number of 1. So hydrogen has 1 proton, and because hydrogen has 1 proton, he has 1 electron circling around on the outside here. So some other examples that we talked about the other week. Carbon, we talked about at the very end of last week, has an atomic number of 6. And so carbon has 6 protons and 6 electrons. On the homework, which most of you guys did pretty well on, fluorine was the very first element on the homework. He had an atomic number of 9. So fluorine had 9 protons and 9 electrons. So the protons and the electrons are always going to be equal to each other. So that's how we can figure out our electron number, how many we have. We just look at the number of protons. And if you remember from Tuesday, the number of protons is told to us by the atomic number of that atom. So like the little number that was in the top of the box, that tells us the protons and the electrons for that atom. So that's kind of a brief summary of all the stuff that we talked about on Tuesday. But one thing that we didn't get to that I want to cover in a whole lot of detail today is this idea that electrons do not just float randomly around the outside of the atom, right? So far we've talked about how they're not in the nucleus, they're kind of around the outside, and there's a specific way that they get arranged around the outside of an atom. They're not just randomly floating around, bumping into each other, doing this and that. They have a structure. There's an order to how the electrons will orbit or go around the nucleus of an atom. So instead of just kind of floating around randomly, instead, they're organized on something called electron shells. So if you imagine the nucleus of an atom as being this like ball of particles in the middle, the electron shells are kind of like invisible outer layers of the electron. So kind of like how onions, you can pick away layer, until you get down to kind of like the core and the center. Same kind of concept with the electrons around an atom. So obviously these guys are not made of like string or actual eggshell or anything like that. They're way too small for that. But there are these kind of invisible layers that surround each atom, the nucleus of each atom. And like I mentioned, there is a very specific way that electrons are arranged in those layers. So everything depends on how many electrons that we have. So for example, hydrogen right here that we were just talking about, he's a super simple atom. He has an atomic number of 1. So he's just got the 1 electron out here. So that electron goes on the first shell of an atom. So as atoms add electrons onto their shells, we start from the first shell, the closest shell to the atom. So the first shell would be this guy right here. And then we expand out to larger and larger shells. So our first shell can fit 2 electrons on it. That's its maximum capacity is 2. So hydrogen only has the 1 electron, so he just has the 1 floating around on that first shell. Helium is a teeny bit bigger. He's got atomic number of 2. So helium has 1 and 2 electrons. So helium has a full first shell, right? Helium's first shell right here, he's got 2 electrons spinning around that shell. That's all that he has. He doesn't have any more electrons, and so his first shell is all totally full. So if we have a full shell on that first shell, but we still have more electrons to go, what happens? Well, let's look at lithium down here. So lithium is the 3rd electron after hydrogen and helium. So he's got an atomic number of 3. So this means that lithium has 3 electrons. We already talked about we can put 2 electrons on that first shell. So electrons 1 and 2 can go on this first shell. But now that first shell is full. No more electrons can fit on there. But we've only put down 2 of our 3 electrons so far. So electron number 3 is going to go on the second shell. So we've got our second shell right here after the first one, a little bit more outside of the first one. And the second shell and the third shell, which we'll talk about in a little bit, they can both fit a maximum of 8 electrons. So the first shell only can do 2, and that's its max. Second and third shells can go up to 8. There are more shells besides just the first, second, and third ones, but we're not going to worry about that for this class. That's a little bit too advanced for what we're dealing with. We're just worrying about shells 1, 2, and 3. So let's look at carbon, for example. Carbon has an atomic number of 6. So carbon has 6 electrons. So once again, if we want to figure out where the electrons will go on which shell, we start with the first shell. So we're always going to start with the first shell, and then we start counting. So we've got electron 1 and electron 2 on the first shell. But now it's full. No more electrons can go on the first shell. only those two. So we have to move up and put the leftover electrons on our second shell out here. So we did 1 and 2 on the first shell, and then 3, 4, 5, and 6 go on our second shell. So now we've put all 6 of carbon's electrons on these electron shells. 2 on the first shell, and then it got full, but we still had some more. And so the leftovers went on the second shell. So carbon has 2 electrons on the first shell and 4, that says second, I know. Writing on a computer screen with a mouse and keyboard is very difficult. There we go. So carbon has 2 electrons on the first shell, 4 electrons on the second shell, which gives us our total of 6. So we put those 2 on the first shell, still had some left over, and so we filled up that second shell with 4. So carbon only has 4 out of the total possible 8 electrons on that second shell, but we don't need to add any more because we already reached his number. We already reached the total number for carbon. If we did want to totally fill up that second shell, we'd have to look at an element like neon. So neon has an atomic number of 10, which means that neon has 10 electrons. So let's figure out where all those electrons for neon are going to end up. So we start on the first shell and we start counting. Neon's got 1, 2 electrons on the first shell, but we still have some more electrons to go, right? 2 is a lot smaller number than 10. So let's move up to the second shell and keep counting. So then 3, so 1 and 2 on the first shell, and then 3, 4, 5, 6, 7, 8, 9, 10. So the remaining electrons fit on that second shell. So in total, neon's got 2 electrons on the first shell and 8 electrons on the second shell. So combined together, 2 and 8 gives us the 10 total number of electrons that neon has. So neon has a completely full first and second shell, right? The shell number 2 right here cannot fit any more electrons on it, which for neon is fine because he's only got the 10, so he's all full on both shells. If we have any more than 10 electrons, we can't fit them all on shells 1 and 2, and that's when we have to expand to our third shell. Right, so neon has 10 electrons, like we were just talking about. Sodium over here has 11 electrons. So just like neon, we can fit 1, 2 electrons on the first shell, and then 1, 2, 3, 4, 5, 6, 7, 8 electrons on the second shell. The 2 and that 8 together give us 10 electrons, but 10 is still smaller than 11. We still have one more electron that we haven't put down yet. shell 1 is all full. Shell 2 is all full. So we have to put electron number 11 on the third shell, right? So I kind of think of it as you're adding electrons to these shells, once they're full, then they kind of start overflowing over into the next shell. So sodium has 11 electrons. So we put 1, 2 onto the first shell. That gets full. So we have to move to the second shell. We can put numbers 3, 4, 5, 6, 7, 8, 9, 10 on the second shell. That's a total of 8 around the second shell. But now the second shell is full and we still have 1 electron left over. So electron number 11 has to go on our third shell. So sodium has 2 electrons on the first shell, 8 electrons on the second shell, and 1 electron on the third shell. And so together, these give us our 11 total electrons. So silicon and argon are essentially the same way as sodium. Silicon has an atomic number of 14, and argon has an atomic number of 18. So with silicon, we put those 2 electrons down on the first shell. We still have some left over. We put those 8 electrons down on the second shell, and we still have some left over because 2 and 8 is 10, which is still less than 14. So those last 4 electrons have to go on the third shell out here. The bottom one is being cut off a little bit on my screen right now, but there's a little electron down here and then over here. So after we filled up shells 1 and 2, we still had 4 more electrons that we had to put on shell 3. And then argon is the same way. He's similar to neon from earlier in that all of the shells of argon are completely full. So he's got 2 on the first shell. That's still a lot less than 18. Argon has 8 on the second shell. So first and second are full. 10, still less than 18. And then argon's got a full complement of 8 electrons around the third shell. So argon has a full first shell, a full second shell, and a full third shell. So his first, he's got 2. His second, he's got 8. And his third, he's got another set of 8. So this is how scientists determine what electron number will be on each shell for an element. You essentially figure out how many electrons there are, and then start filling up shells from the first outward. So if you fill up the first shell with those 2 electrons and still have some left over, move on to start filling up the second shell. If you fill up the second shell with those 8 electrons and you still have some electrons left over, that's when you start filling up the third shell. And like I said before, obviously there are much bigger atoms out there than argon with a lot more shells, but we're not going to worry about all of those for this class. We're just going to focus on shells 1, 2, and 3. All right, so I know that that is a lot of information all at once, and it can be a little bit tricky figuring out what exactly is going on with all of these electrons. So are there any questions so far about how we're figuring this out? I'll do a couple more examples of these atoms and these electrons on the next slide But before we get there, is there anything that you're still confused about, still not sure about, still want clarification on?
So if you say like how many electrons are in the outer shell or the inner shell, we would have to count all those and it would be the whole amount that's on there, correct?
Mm-hmm. Exactly.
Okay, that's what I'm trying to make sure.
Mm-hmm. Yeah,
thank you.
Precisely. So if you want to figure out how many electrons are on a certain shell, then if you can do it in your head, that's great. Or if you have to sketch it out on paper, you can just start drawing out those little beads, the little electron beads, and do just like what I've been doing. Count from the first one. Once that's full, move to the second. Once that's full, move to the third. All right, good question, Alicia. Thank you very much. Any other questions about these electron shell stuff before we move to some more examples? Oops. All right, doesn't look like anything is coming up in the chat either. So, promised I'd give you guys some more examples. Hold on. There we go. All right. So a couple more examples to hopefully help drive this home. So nitrogen is element number 7. So he's got 7 electrons. So if we want to figure out the shells, we start counting up how many are going to go on each shell. So I've got our nitrogen nucleus right here in the middle. We've got electrons 1 and 2 right here, but 2 is less than 5, or is less than 7, excuse me, so we gotta still keep going. So electrons 3, 4, 5, 6, and 7 are gonna go on the second shell. So if we count them up, we can see that nitrogen has got 2 electrons on the first shell, and then the remaining 5 electrons went on the second shell, and 2 and 5 together give us that total of 7 electrons that we said are in nitrogen. So again, figured out our number, counted up from each shell, and as soon as one shell got full, we moved on to the next one. We talked about neon in a little bit of detail on the earlier slide. He's got the completely full rows 1 and 2. So he's got the 2 and the 8 to give us 10. But let's look at aluminum over here. So aluminum has 13 total electrons. He's atomic number 13. And so he's got more than neon, which to me is going to suggest that we're going to have to start using our third shell for aluminum. So to figure exactly how much, let's start counting. So 13 electrons in aluminum. Start on the first shell, 1 and 2. First shell is now full. 2 is less than 13, so we got to start adding electrons to the second shell. 3, 4, 5, 6, 7, 8, 9, 10. So now we've put down 10 electrons total, 2 on the first shell and 8 on the second shell. But now we filled up shell number 2. We cannot fit any more electrons on the second shell. So because of that, and since 10 is still less than 13, our last electrons will go on our outer shell. So numbers 11, 12, and 13 go on shell number 3. Now we have finished putting down all the electrons that aluminum has. We've made sure that we filled up the first shell and the second shell before we moved on to the third shell. And so because of that, we are able to determine that when you break it down by shell, aluminum has 2 on the first shell, 8 on the second shell, so you got all full, and then 3 on the third shell. And so 2, 8, and 3 together give us our total of 13 electrons for aluminum, with 3 of those being on the very outside shell out here. All right, so again, if you want to figure out how many electrons go on the different shells, like you're going to have to do for an atom in the assignment for today, it's all about just counting it out and going from one shell to the other one only when it gets full. So like nitrogen and neon did not need a third shell because they are able to completely fill up their first shell and then partially fill or fully fill all of the electrons on their second shell. Ooh, I think it's starting to rain over by my house. That's exciting. All right. So I'll do another brief pause right here. Any more electron shell based questions? Anything that you're still a little bit confused about or not sure about when it comes to figuring out these electrons and their shells? All right, I'm not hearing any questions come in over the mics, and I'm not seeing anything pop up in the chat so far. So hopefully, now that I've gone through it a bunch, it's not as confusing or complicated, or it might have looked if you just glanced at it. One thing that I do want to mention, like one of my students yesterday when I was going through this brought up, is that I mentioned it a little bit before, but these shells are not actual physical areas, right? It's not like a string or a pathway that the electrons are moving along. Essentially, it's just distances from the nucleus of an atom that scientists noticed that at this short distance, there are only ever 2 electrons that were moving and orbiting around the atom at that distance. And then at this little bit further away distance, there were up to 8 electrons that were orbiting around. So these electrons are constantly moving. They're constantly kind of zooming around each other and around the atom. But depending on what shell they're in, determines kind of how far away from the atom that they are moving. All right, it's almost like invisible traffic lanes. So the first 2 electrons only stay in that first lane. The next 8 electrons only stay in the second lane, so on and so forth. All right, so the final couple things that I want to go over with you guys today are related to these electrons and their shells. Hold on, let me get all this purple stuff off the screen. That doesn't make sense anymore. So one thing that scientists noticed about when atoms would interact with one another, there we go, is that atoms really want their shells to be full. So what I mean by this is that obviously atoms cannot have like wants or needs or desires, right? They're not people or animals or plants. They're tiny, tiny microscopic particles. But this is kind of how I think about it in terms of how atoms are a lot more stable when they have a completely full outermost shell. So atoms really want to have a total set of 2 electrons in their first shell and then 8 electrons in their second and third shells. And when naturally this doesn't happen for them, they'll react with other atoms and make different combinations of electrons in order to try to get their shells as close to being full as possible. So some basic examples of this are things like hydrogen. Remember, hydrogen was our super small guy. He's only got the 1 electron in his outer shell, and that makes him a little unhappy. He wants there to be 2. So when you find hydrogen out in the world around us, it's almost never, ever, ever just one single hydrogen atom on its own. Instead, 2 hydrogens will pair up and share their electrons with each other. And so when they do this, both hydrogen feels like they have a full first shell. So because one hydrogen is sharing its 1 electron and one hydrogen is sharing its other 1 electron, both hydrogens feel and act like they have 2 electrons in their outer shell, one that is theirs and one that they're borrowing. Another good example of this is the reaction between sodium and chlorine. So sodium we talked about a little bit earlier. Let's see. Yeah, here he is right down here. Sodium has 11 electrons, which means that there's only 1 electron in the very outermost shell of sodium. So sodium only has 1 electron on his outer shell. Chlorine, on the other hand, has 7 electrons on its outer shell. So because sodium only has the 1, and chlorine has all but 1 filling up its shell, sodium will donate its electron to chlorine and form a bond where sodium has a completely full second shell and then donates this atom to chlorine, this electron to chlorine, so that chlorine can have a completely full third shell. So by filling up their shells, either by getting rid of extra atoms or, extra electrons, or taking in electrons in order to complete kind of their set on their outer shell, the atoms can react with each other and become more stable afterwards. So I'll talk about this concept actually in a little bit more detail during one of the notes next week, but I wanted to introduce it to you guys here about this idea of atoms wanting their shells to be full and sharing their electrons so that that happens. So how easily an atom is able to share its electron from one to the other is known as its reactivity. So reactivity is a chemical description of an atom that describes how quickly and how easily is this atom going to react or combine with other atoms, essentially. So like I was mentioning with sodium and chlorine earlier, those are both very, very reactive atoms because sodium and chlorine will very quickly and readily react with elements and compounds that are around them. So in general, elements that have a very, very empty outer shell, like sodium here, he's only got the 1 electron on his outer shell, or elements that have a almost full outer shell, like chlorine over here has almost a complete set of electrons on his outer shell. These elements tend to be the more reactive elements. So essentially, it's like the way I kind of think about it is like they want so badly to have that full outer shell that they will very quickly either get rid of or accept electrons coming in order to make that happen. And because they're able to do that really, really quickly and easily, they're known as very, very reactive atoms. So like this picture over here, if you take a small block of pure sodium, it is so reactive that you usually have to keep it sealed off, because when it comes into contact with air, it will violently react and create all of this light and gas and stuff coming out. Because it is so reactive, it is so easily willing to give up that electron, make a chemical reaction happen so that it can be set with just its full second outer shell. Again, we'll talk about this in a little bit more detail a couple days into next week, but I wanted to kind of bring it up now so you have it kind of rattling around in the back of your mind for when we get there. So on the periodic table that we were talking about on Tuesday, it has all these little boxes and stuff that we mentioned. The way that it's organized is that all of the elements that are in a column with each other, also known as a group, have similar reactivities. So like lithium and sodium and potassium and rubidium all have very similar reactivities to each other. They're all very, very, very reactive. Another group over here, group 18 over on the far other side, things like neon and argon and krypton, they are very, very, very non-reactive. They will barely react with any other types of elements, no matter how hardly you try. So this is true for every single column in the periodic table. All of the elements in a column are similar to each other in terms of how they react with other atoms when given the chance. So the last thing that I kind of wanted to talk about with you guys today, and the thing that your homework for tomorrow is going to be based on, is the concept of kind of separating our elements out into three basic types. So on this chart, you've seen all these colors, and they actually correspond to which type of element that we're looking at. So the metals are the ones that are colored in yellow. You'll see that they make up the vast majority of the periodic table, and especially in the left-hand and middle sections. The nonmetals are in green, kind of clustered over here on the right, with one little guy, hydrogen, hanging out up here. And then finally, the metalloids are this sort of weird in-between group that has this kind of zigzag action over here, literally in between the metals on one side and the nonmetals on the other side. And so we're going to go through just some basic descriptions, basic characteristics of how these guys are similar and different from one another. So first up, because they're the most common, we're going to talk about the metals. The metals are also sort of the easiest to think about in terms of their properties. So like I like to picture, when I'm trying to think about the properties of metals, I like to picture a bunch of aluminum foil, right? Because it has a lot of common metal properties, because aluminum, right over here, is an element that is a metal. So metals tend to be shiny, right? They tend to be very reflective of light. And for the most part, they are solid at room temperature. So at like 70, 75 degrees, most of the metals that we find on Earth are in the form of solids. So like aluminum foil, tin cans, lead pencils, all of that is solid material. There are a couple cool exemptions. So mercury is one of the few metals that is actually liquid at room temperature. So when it gets just a little bit warm, it is no longer a solid and it looks like shiny water, essentially. It's really cool to look at, but don't touch it. Mercury is very toxic if it gets into your body. So shiny solids for the most part. Metals are what's known as malleable and ductile, which means that you can work with them pretty easily without them like breaking and shattering into pieces. So malleable refers to being able to hammer metals down into like flat sheets. So if you think of, again, the aluminum foil example that we were talking about a little bit ago, that is a metal that's been completely flattened down into something that's roughly the same thickness as like a big sheet of paper, right? Other elements that I'll talk about a little bit later might totally shatter if you try to do this, but metals, you can kind of squish them down into one sheet. Metals are also ductile, which means that like things like copper that are used for electricity going to your house, we can pull them out and stretch them and kind of twist them and turn it into a wire. Again, this wouldn't be possible if we weren't able to work with the metals so easily. And then one of the most important characteristics of metals is that they have a very high conductivity. And what this means is that they can move heat or electricity very, very quickly and easily from one area to another. So this is why all of your frying pans, right? You don't have any frying pans made out of plastic or wood. They're all made out of metal, because when you put the frying pan on the hot stove, it'll heat up pretty quickly and the whole frying pan will get hot. It moves that heat all around all evenly. Same thing for electricity. The reason why all of the wires that are going in telephone lines and going into your house are made out of metal is because metal wires can move electricity really quickly and easily from one place to another. So if you think of like the sockets in your house, right? If you have like a plastic fork or a wooden stick and you stick it into the socket, nothing's really gonna happen, right? I mean, I would suggest that you don't do that. It's not a great idea, but you're probably not gonna get seriously injured in the process, because things like plastic and wood are bad conductors. They do not move electricity very easily. However, you get like a metal knife or a metal fork and you stick that into your socket in your house, and you're gonna have a real bad time, because all the electricity going through your wiring in your house is gonna be able to very easily pass through that metal fork or knife and into your body, which is not good. That's not a good place for a whole bunch of electricity to be. So metals are shiny, they tend to be solids. We can hammer them and squish them down and twist them up into wires fairly easily. And they're very, very, very good at moving heat and electricity around. So on the flip side of this, the type of element that has almost all the opposite properties as metals are, you might expect, nonmetals. So nonmetals are not shiny, right? They tend to be very dull, kind of almost if you think like bricks or rocks, that's kind of what we mean by dull. They're not really shiny, they're not glistening in the sun. They are very poor conductors. Nonmetals do not move heat and electricity very well. So like the plastic and wooden materials that we were talking about earlier, that if you stick in a light socket, it's not a huge deal. Plastic and wood are both mainly made out of carbon, and carbon is a non-metal element. So not very good at conducting. Nonmetals, for the most part, are gas at room temperature. So think like, so while carbon is one that is not gas, most of them like helium, oxygen, hydrogen. What was one that I was just thinking of? Nitrogen. All of these guys are nonmetals, and all of them are gases at room temperature, right? So they make up a lot of the atmosphere that's around us, and so we can't see them really get solidified unless we make them super, super, super duper cold. The solids of nonmetals tend to be brittle. So they tend to be kind of rock-like. Like here's sulfur over here. Sulfur is one of the few solid nonmetal elements at room temperature. But if you try to take sulfur and smush it down into a plate or pull it out into like a long sulfur wire, it's just gonna break. It's gonna shatter into 1,000 pieces in your hands. Nonmetals do not have those malleable properties of metals. They're very, very rock-like when they're solid. So they break, they chip, they shatter. They don't squish and bend very easily. All right, so pretty much like I was saying, metals and nonmetals are kind of on opposite sides of the spectrum when it comes to their properties. So there are a handful of elements that have some kind of metal qualities and some kind of non-metal qualities. They fall sort of in the middle, and those guys are the metalloids. So they're in between metals and non-metals. Similar to metals, metalloids tend to be solid at room temperature, right? They tend to take a definite shape. But similar to non-metals, they are often very brittle and hard. So it's hard to work with metalloids the same way that you work with metals. They're much more prone to chipping and shattering. So metalloids can work as very good conductors, but it's only under very specific environmental conditions. So scientists gave them the name of semiconductors. So you may have heard of semiconductors before, especially around Austin, because they are very important for computer chips. They do conduct electricity extremely efficiently and rapidly, but they only do it under very specific temperature and pressure and humidity conditions. All right, metals will conduct anything at just about any time. Semiconductors can only conduct under very, very specific circumstances. So silicon is a very common semiconductor. Not only is there a lot of silicon in sand and the glass that makes up your windows of your car and your house are mostly made out of silicon, but there's also a lot of silicon in computer chips. So this is the reason that the area outside of San Francisco, where a lot of the big computer companies are located, is called Silicon Valley. So like Facebook, Google, Apple they all have sort of their main campuses in the same general area of California. And so in the 80s and 90s, when computers were really starting to take off, people nicknamed that area Silicon Valley because of all the different types of computer chips that were being produced over there. All right, so solids, shiny, squishable, good conductors, or not solids, metals, excuse me. Non-metals, opposite side of the scale. Brittle, will shatter, don't really conduct, tend to be gas. And then metalloids kind of have some characteristics of one and some of the other. Like I mentioned before, there's not a ton of metalloids, and they do literally fall on the periodic table in between the metals and the non-metals as well. So earlier I was talking about how each column of the periodic table has elements with similar reactivity. So they're similarly easy to be able to get them to react with other elements. For the metals, the left side of the metals is where the most reactive metals are. And then as you move towards the right side of the metals, excuse me, so over on the right, you get lower and lower and lower reactivity over here. On the flip side, when we go to talk about the nonmetals, the little green guys over here, nonmetals tend to be the lowest reactivity in the first couple columns of the nonmetals. And then as you get closer to the right, you get more and more and more and more reactive. unless you go all the way to the far right-hand side. So I mentioned earlier that these guys have totally full first or second or third shells. And so they have extremely low reactivity. So like these guys right here in column 17, fluorine and chlorine and iodide, these guys are extremely reactive nonmetals. But once an element gets that one more electron, it has a full shell, and so it becomes an extremely unreactive nonmetal. So some important nonmetals that I wanted to bring up, either because they have an interesting name or they're super important for life, are carbon. So carbon's right here. He's number 6 on the periodic table. And carbon is the element that pretty much all life on Earth is based on. So the food that we eat and the energy that we get from that food is all based on carbon. The structures that have built up not only humans, but also all other plants and animals that have been discovered so far are all based on carbon-based structures. So carbon is probably the most important when it comes to building out bodies of plants and animals here on Earth. And then finally, just one kind of interesting note, that very last column, so that those guys in column 18 that do almost no reacting with anything else, they have an interesting name of the noble gases, because when scientists were first studying them and first determining that they were not willing to react with other elements, they started to think of the gases, these gases, as being kind of very like high society, like very noble and snotty, and being like, oh, well, we're too important to mingle with all of these other elements that's over here. And so they got the name of noble gases because the scientists were like, they're kind of like noble lords and ladies that don't want to mix with all these other commoner elements that make up the rest of the table. So just a fun little kind of sciencey fact about those guys on the very end here. So things like neon and xenon and krypton that we were talking about the other day, all of those guys are noble gases, extremely non-reactive to the other elements because they have those full outer electron shells. Alrighty, and I believe that brings us to the end of our electron shell and reactivity notes. So any questions on anything that we've talked about today so far? Either the electrons and their shells, the stuff about reactivity, the differences between the metals and the nonmetals, any stuff like that. Anybody have any questions on that so far?
So for the metals and like non-metals that you were showing us, is that going to be on tomorrow's work?
Mm-hmm.
Okay, so that's just basically like a review for tomorrow.
Exactly.
Okay. Thank you.
All right, good question. And I can actually go ahead and show you guys what today and tomorrow's work is going to look like if you want a little peek. So for the assignment for today, again, remember, since you guys were awesome and came to the Zoom meeting today, that means you got your attendance already, so you don't have to do this assignment until later. If you don't want to, you don't necessarily have to finish it by the end of the day. Make sure you get it finished up sometime soon. So it's asking specifically about the element oxygen. And it's a little bit of stuff from Tuesday and a little bit of stuff from today. So we have our periodic table box for oxygen right here. And I want you guys to use this information to figure out not only how many protons, neutrons, and electrons does oxygen have, just like you were doing for the assignments the last couple days, but then also I want you to tell me how many electrons go on the first shell around oxygen, how many electrons, if any, belong on the second shell of oxygen, and how many electrons, if any, belong on the third shell of oxygen. So it'll be up to you guys to figure out where do the electrons go around oxygen, and then count up how many are on the first shell, how many are on the second shell, and how many, if there are any, on the third shell. All right, any questions about the Thursday assignment? All right, so then that is the assignment that just got posted earlier this morning today. And then tomorrow's assignment for your Friday attendance is a comparison of metals, metalloids, and nonmetals. And so there's basically a list of descriptions over on this first column over here. And then for each one of these descriptions, I want you to tell me, does this description fit metals and or metalloids and or nonmetals? So like it says in the directions, there could be more than one substance that matches the description. So for example, if you thought that metalloids and nonmetals were both gas at room temperature, then you'd put a check mark for metalloid and check mark for nonmetal. So essentially for each one of these descriptions, you're going to put a check mark in each box that you think it fits the type of element. So this is what the Google Form version of the worksheet looks like. The Google Doc version, if you prefer to do it that way, is the same thing essentially, just a little bit differently arranged. And so we still have the descriptions on one side and the types of elements along the top. The only difference for this one is that you can't really put check marks in these boxes easily. So instead, I just want you to go through each box and write yes or no in each one. So instead of going through and being able to put in checks, you're just writing either yes, this does match with that type of element, or no, it does not. So either way that you want to do either the form, writing down, or the Google Doc, excuse me, writing down yes or no, or the form, checking off the boxes that you think fit. Both of those work for me. And so that is the assignment that is going to be coming up on Friday, tomorrow, for your Friday attendance. So again, if you ever want to look back at these notes, they're posted here under the 9/17 Thursday notes section with the electron shells. And then after we're done today, I'll post the recording of our Zoom meeting right here in the electron shells meeting recording tab. All right, we've only got a couple more minutes of class before I gotta let you guys go. Anybody have any final questions to wrap up the material from today? All righty, sounds like you guys have pretty much got it down. Again, if you ever do have any questions, feel free to text me, shoot me an email, or make a comment on one of the assignments on Google Classroom, and I will get back to you as soon as I possibly can.